Okay, welcome to week 5. In Module 4e, we're going to take a look at errors that occur during hypothesis testing. These have the not very informative names type 1 and type 2 errors. We're also going to take a look at what are called p-values and describe what those are about. Okay, so at a little finer level of detail, we're going to take a look at how you select an appropriate level of significance for your hypothesis test. It is true that 0.05 is kind of conventional, but that's not a good level to use in all possible cases. We're going to take a look at what type 1 and what type 2 errors are, and also how to balance the trade-offs between type 1 and type 2 errors, which at this point tells you nothing at all, but we'll get there shortly. We're also going to introduce what are called p-values and talk about how to interpret those. And as with z-scores, there's going to be a difference in what p-values mean for one-tailed versus two-tailed hypothesis tests. Okay, so we've been using significance levels for our hypothesis tests. We need to be absolutely clear about the correct interpretation of that significance level. Let's suppose, as shown in our diagram here, that the mean of the population is some value mu naught, and our null hypothesis is that the true mean is mu naught. So in this case, the null hypothesis is true. Okay, the null hypothesis is that the mean is mu naught, and the null hypothesis is true. Now, because the sampling distribution of the means of samples is normal with the mean mu naught, it is more likely that when we draw a sample and compute the mean of the sample, that mean is going to be near the true population mean. It is less likely that the mean of that sample is going to be far away from the population mean. But because the distribution is normal, it is possible that we will draw a sample whose mean is far away from the population mean. And when we select our significance level, here we're selecting a significance level of 0.05, and we use the critical value tool or table to find that the z-score for that is 1.645, all right? The way our hypothesis testing works is if the sample that we have selected has a mean that is to the right of that z-score, 1.645, we will reject the null hypothesis with a 5%, a 0.05 significance level. But what have we done? We have now rejected a true null hypothesis because by bad luck, we selected a sample whose mean was far away from the true mean. Okay, so the correct interpretation of the significance level alpha is that it is the probability come on, mouse, there we go. The probability of incorrectly rejecting a true null hypothesis. Okay, the probability of incorrectly rejecting the null hypothesis that the mean is mu naught when the null hypothesis is true. All right? This is often misinterpreted as the probability that the null hypothesis is true. So we might misinterpret that if we get a value out here above this critical level, that means that there's only a 5% probability that the null hypothesis is true. That is not a correct interpretation. Okay, so anytime we try to make inferences about population parameters like mean and standard deviation based on some sampling, there's inherent uncertainty, and there is always going to be some kind of error that can creep in. Here's a table that differentiates kinds of errors that can occur. In reality, there are two possibilities. Either the null hypothesis is true or the null hypothesis is false. Okay, so the null hypothesis being either true or false, you know, these are mutually exclusive and exhaustive. One of them has to be true, and only one of them can be true. Now, when we do a hypothesis test, the decision that we make, again, can be one of two possibilities. We can either not reject the null hypothesis, or we can reject the null hypothesis. Now, the kind of error that we just described is where we reject the null hypothesis even though the null hypothesis is true. And that, with a total lack of imagination, is referred to as a type 1 error. All right, sometimes, you know, I wish there were more intuitive names for various things in statistics, and this is one of them. But a type 1 error is the kind of error where you reject a null hypothesis even though the null hypothesis is in fact true. But there's another kind of error that can occur. If the null hypothesis is false, and we fail to reject that null hypothesis, that's another kind of error that's referred to as a type 2 error. Okay, so here we're doing a hypothesis testing. In this first instance, the null hypothesis is true, that the true mean is this mu naught value, and we set our critical value according to the alpha that we have chosen. If we do get a sample whose mean is above the critical value, then our rule is that we reject the null hypothesis even though the null hypothesis is true. On the other hand, if the null hypothesis is actually false, we still have to set a critical value beyond which we will draw the conclusion that the null hypothesis is false, or at least we will accept, we will reject we will reject that the null hypothesis is true. And in this case, if we draw a sample below the critical, you know, whose mean is below the critical value, we will conclude that the null hypothesis is true, or that we can't reject the null hypothesis, even though the alternative hypothesis is true. The null hypothesis is false in this case. All right, so we're always going to have, because we can't ever be, you know, completely perfect, we're always going to have some amount of type 1 error and some amount of type 2 error. So let's have alpha be our probability that we're going to make a type 1 error. Now alpha, I mean, that is how we define alpha, basically. Alpha is the probability within the tail of the distribution, and in this case, we are, again, doing a one-sided hypothesis test. Okay, so the area under this part of the curve, the area under the normal distribution above our critical value, is our significance level, whether it's, you know, 0.05 or 0.1 or 0.10, sorry, 0.01 or 0.10 or whatever it might be. If we draw a sample and the mean of the sample is is in that critical region, then if the null hypothesis is true, we will have committed a type 1 error. And in fact, we know that the probability that we will commit a type 1 error in the case where the null hypothesis is true is this significance level that we select in advance. Now, on the other hand, let's suppose that the null hypothesis is false in reality, which means that the alternative hypothesis is true. We will set a critical level at which we're going to reject the null hypothesis. But in this case, if we draw a sample and the sample mean is below the critical level, even though H0 is false, we are not going to reject that false null hypothesis. And the probability of doing that is labeled by beta here. Now, what about beta versus alpha? Well, alpha, we know the meaning of alpha. Alpha is the probability that we will reject a true null hypothesis. We know from the central limit theorem that if the null hypothesis is true, that the sampling distribution will be normal around the population mean with a certain standard deviation, etc., and we can therefore compute an exact value for that critical value, and we know for sure what the probability is that we will produce a type 1 error by rejecting a true null hypothesis. For the alternative hypothesis, though, all of this stuff is really unknown. If we know that the null hypothesis is false, well, assuming that the null hypothesis is false, then we know that the population mean is going to be somewhere other than at the null hypothesis mean, the mean dictated by the null hypothesis assumption. But we don't know exactly where the true mean is if the null hypothesis is false. So the true mean is somewhere. We draw our critical value based on the assumption that the null hypothesis is true. And if we fail to get a sample that is above that critical value, then we accept the null hypothesis, and the probability of erroneously accepting a false null hypothesis is defined by this area beta, which we have no way to compute. Okay, so this is polite. Beta is hard to calculate. Yeah, beta is generally pretty much impossible to calculate. But we know there are type 1 errors, and we know that there are type 2 errors. Okay. Also, and this is very important, there's a trade-off between type 1 errors and type 2 errors. Okay? Here is our probability distribution of the sample means, assuming that the null hypothesis really is true. Now, if we decide that we want an even stricter test before we reject the null hypothesis, we can move our critical value higher, maybe to a alpha of 0.01 instead of alpha of 0.05, and that will reduce the probability of rejecting a true null hypothesis. The problem is that if the null hypothesis is false, that same movement to the right of the critical value is going to increase the probability of making a type 2 error in the situation where the null hypothesis is false and therefore the alternative hypothesis is actually true. All right, so we know alpha. We specify alpha, and we can use the central limit theorem to figure out critical value and all that good stuff. We don't know the details of what's going on with the alternative hypothesis, and we have a hard time estimating what the probability of a type 2 error is. Now, there are, however, severe consequences sometimes for either type 1 and or type 2 errors. Okay? So here we have a test of understanding. A computer supplies retail... I misread that. A computer supplies retail chain has a policy of only opening stores in communities where households spend more than $40 per year on computing supplies and equipment. Okay, we've actually seen this example before. All right, and so we're going to assume the null hypothesis, which is that the community does not spend more than $40 per year. So our null hypothesis is that the true mean for a given community is less than or equal to 40, and our alternative hypothesis is going to be that the sales is greater than $40 per year. Okay, so what is the type 1 error in this problem? Well, the type 1 error in this problem is that we reject a true null hypothesis. What's the consequence? Well, if the null hypothesis is true, that means that the average sales within the community per household is actually less than or equal to $40, and it means that we should not open a store there. But because of the type 1 error, because of the probability of a type 1 error, there's going to be that probability that we will fail to reject the null hypotheses and instead accept the alternative hypothesis and accidentally build a store where we shouldn't build a store. Okay? And so we will up front, we will lose a lot of money. We will spend a lot of money just building the store and hiring employees and on, and it may turn out that that store performs very badly and needs to be shut down. What, on the other hand, is a type 2 error? Well, a type 2 error would be, suppose that the alternative hypothesis is true and that the null hypothesis is false, but we fail to reject that false null hypothesis. Then we have an opportunity cost. We don't build the store. We don't spend any money up front, but we also don't, achieve any profits from sales that we have forgone. Okay, how can we reduce the probability of making a type 2 error without increasing the probability of making a type 1 error? Well, the probability of making a type 1 error is the alpha that you choose. It's the significance of your hypothesis test. You can reduce the probability of making a type 2 error for a given type 1 error probability by increasing the sample size, and that will reduce the probability of a type 2 error. On the other hand, it may be impossible to increase a sample size after the fact if you've already gone out and collected your data, or if you haven't, it may be quite expensive to collect more data. So there's there's no such thing as a free lunch, as we've seen before in these notes. All right, so we need to balance the impact of the type 1 and type 2 errors in our hypothesis testing. what we mean by balancing here is we need to quantify the costs of making a type 1 error and quantify the costs of making a type 2 error. And then we choose alpha, and we can also choose a sample size to come up with an appropriate beta that balances out the costs here. Now, if we think about, our very original hypothesis test, this was the lady drinking tea. And the hypothesis was that she could not tell the difference between whether milk was added first or whether tea was added first. And we chose an alpha of 0.05. Well, we didn't, but Fisher chose an alpha of 0.05 as the probability of rejecting a true null hypothesis. And he decided that doing 8 experiments, having a sample size of 8, was going to be sufficient to make a decision about whether to reject the null hypothesis or not. That is, whether to accept that she could actually tell the difference. Now, what is the cost of either of the errors in this situation? What is the cost of concluding that she can tell the difference when she can't? Or what is the cost of concluding that she can't tell the difference when she can? Well, there's no cost, right? This is just an intellectual curiosity. There's nothing at stake. Nobody's health, nobody's life savings are in any way at risk as a consequence of doing this experiment. So choosing a 0.05 alpha, hey, what the heck? That means that if she's guessing, there's only one chance out of 20 that she's going to guess well enough that she'll fool us into believing that she can actually tell the difference. But on the other hand, what if you're doing a test of an investment algorithm or a test of a drug or some kind of medical device, and a type 2 error results in somebody losing their life or losing one of their limbs or losing half of their money? Well, in that case, you'd really better be very careful about cranking your sample size way up to reduce the probability of type 2 error. All right, so it's always a trade-off is the bottom line. Okay, well, next we're going to take a look at p-values. This gives us a quantitative way of measuring the strength of evidence to support our conclusion about a hypothesis test, whether to reject the null hypothesis or fail to reject. Rather than specifying an alpha in advance and then just making a binary decision about whether your sample indicates that you should reject the null hypothesis or not, the p-value allows you to determine whether accepting or rejecting was a close call or an obvious thing. Let's see how that works. Okay, so to begin with, I'm just going to read this definition of what a p-value is, and it will probably not make any sense to you. Then we'll take a look at an example and re-look at the definition, and hopefully it will become more clear. So the p-value is the smallest level of significance for which the observed sample statistic tells us to reject H0, the null hypothesis. Easy as pie. Well, no, not really. All right, so let's look at a specific example. Let's suppose that our null hypothesis is that the mean is less than or equal to 0, and our alternative hypothesis is that the mean is greater than 0. All right, so here we have the mean of 0, and for an alpha of 0.05, we discover that our critical value is 1.65. Therefore, if our observation produces a z-score that is 1.65 or greater, under our rules about hypothesis testing, we will reject the null hypothesis and accept the alternative hypothesis. Okay. So we take a sample and we discover that the mean of the sample is 3.5. The standard deviation is 24. The number of observations in the sample is 144. And so we do our computation, 3.5 minus 0 divided by 24 over 12. Okay, so that works out to 3.5 divided by 2. 3.5 divided by 24 over 12 is 3.5 divided by 2, which gives us a z-score of 1.75. Check it out. I could do math in my head there. Okay. Well, 1.75 is past our critical value of 1.65. And so we would say that because the value that we computed for our z-score is greater than 1.65, we reject the null hypothesis at a significance level of 0.05. But actually, we can use this value, 0.04, as a critical value itself. And we can simply say, okay, the p-value is 1.75, meaning that the probability that we reject a true null hypothesis is actually only 0.04. So we can just say that, all right, that p-value is our smallest alpha, our smallest value for alpha, at which we can reject that null hypothesis. In other words, because the p-value is less than or equal to alpha, we reject our null hypothesis. All right, so now let's try reading this definition again. All right, so the p-value is the smallest level of significance for which the observed sample statistic tells us to reject H naught. In this case, our p-value was 0.04. And because our z-score was 1.75, which means that the probability of everything to the right is 0.04, we can say that our p-value is, our p-value, the lowest value of significance at which we can still reject the null hypothesis, is 0.04. Okay, now I've just realized that this p-value 0.04 may seem like it just fell from the sky. Let's see where we got that from. We computed our z-score of 1.75, and if I pull up my normal distribution widget and set the mean to 0, standard deviation to 1, this is a z-score, so we're looking at a standard normal distribution. When I plug in the specific z-score of 1.75 as my lower bound for probability of something being greater than that, this is where I get this probability of 0.04. Okay? Whereas 1.65 is where, as we probably have memorized, is where we get the 0.05 from, you know, approximately. Now, let's try let's try a different observation. Let's suppose that from our sample we get a mean of 3.0 instead of 3.5. Well, the z-score corresponding to an observation of 3.0, all right, that's going to be 3.0 divided by 24 over square root of 144. In other words, 24 over 12 is 2. 3.0 over 2 is 1.5. So now we're going to have a z of 1.5 rather than 1.65 or 1.75. And the p-value for that is 0.06668 or 0.067. So we can report that the p-value when x bar is equal to 3.0 is 0.67. That doesn't get us into our critical region, but we might scratch our heads and decide, that's not too far above 0.05, so let me consider whether I need to do a little bit more investigating to see whether we should reject H0 or not. It kind of puts us near the fence of whether we might want to reject the null hypothesis. Okay. Onward ho. Well, okay, so this, okay, this is amusing. This is the example that I just made up out of thin air. If x bar is 3, that gives us a z-score of 1.5 and a p-value of 0.067. Okay, so we are not going to reject under our original rule, but we still can report the p-value rather than just announcing that we're not rejecting the null hypothesis. On the other hand, if we have an x bar of 5, that gets us a much larger z-score of 2.5. And let's try plugging that z-score of 2.5 in. Is a very small value, 0.0062. According to my widget. Okay, and so that would be 0.006 is so much smaller than 0.05 that we can say we reject the null hypothesis, with a p-value of 0.006, which is a very significant rejection. Okay, now customers, bosses, clients, the general public and so forth are often not very happy at being told numbers about things, significance levels and whatnot. So we often translate various levels of significance or lack of significance into words. All right. So in the case where we got a z-score of 1.75 and the p-value is therefore 0.04, and that p-value is less than the alpha, we say that we're going to reject the null, and we describe the alternative hypothesis as being statistically significant. Okay, so the alternative is statistically significant in this case. Now, on the other hand, if we get a p-value that's greater than our significance level, we don't reject the null, and we say that the alternative is not statistically significant. Okay, these are pretty bland statements. Statistically significant, not statistically significant. In both of these cases, the p-values that we computed are somewhat below and somewhat above our alpha of 0.05. If we get a very small p-value, we could describe the alternative as highly significant, On the other hand, if we get a p-value that's just a little bit bigger than alpha, we could translate that into words and say, well, it's almost significant. It's not significant at an alpha of 0.05, but it's almost significant. So we're placing value judgments on these numbers now. Here, if we got a p-value of something like 0.31, which is way worse than 0.05, we might say that this is not even close to being significant. All right, so the p-values are directly very useful to statisticians because they are a much better descriptor of what's going on, as opposed to just saying, well, it's above 0.05, so I reject the null, or it's below 0.05, so I don't reject the null. The p-value gives the statistician more information. And it also enables us to translate into words that convey better meaning to people who are not statistically trained. All right. We can also do p-values for two-tailed tests. In this case, we're rejecting the null hypothesis if we are far from the mean in either direction. I don't think I'm going to go through those details there. Likewise, we can compute a p-value. Now, the p-value tells you the probability for one side when you're doing a two-tailed test. So you need to double the p-value before you compare it to your alpha to see whether the p-value is less than the alpha, meaning that it's significant, or greater than the alpha, meaning it's not significant. All right, let's take a look at doing hypothesis testing and calculating p-values in ISLE, just to understand how to do this. We're going to use our fast food data set. So let me pull that up. Fast food experiment. Okay, and here are all the various columns. Now, cal info indicates whether the particular subject was or was not given calorie information. I might be interested in knowing what proportion of the test subjects were given calorie information. It wouldn't be absolutely necessary to give half of the people calorie information, but in a situation like this, that's the most reasonable thing to do, is to give half the people calorie information and not give the other half calorie information. So this is going to be a hypothesis test about proportions. Let me pull up my toolbox of statistical stuff I can do, and now I want to do a test, and I have one sample of data, and I want to do a proportion test. Okay, there are 1 and 2 sample mean tests, 1 and 2 sample proportion tests. 2 sample tests we will take a look at in the next module, but let me select the 1 sample proportion test, and my hypothesis is going to be that the proportion of people given calorie information is 0.5. My alternative hypothesis is therefore going to be that the proportion is not 0.5, that it's either significantly greater than 0.5 or significantly lower than 0.5. So let me choose cal info as my variable. I can choose 1 to mean that they were given calorie information. Actually, I guess to be consistent with the example, I'll choose 0, which indicates that they were not. But we expect the proportion who were and the proportion who were not to both be 0.5. This is a two-sided test because we're interested in testing whether the proportion is far away from 0.5. And now I will do my calculation and scoot this toolbox window over. All right, and so we're testing the population probability that cal info is 0. The specific hypothesis we're testing is that proportion is 0.5 as a null hypothesis, or that it's not 0.5. We compute that the sample proportion of not receiving calorie information is 0.48, and we get a two-sided p-value of 0.30. All right, now that is not a very significant p-value. Our 95% confidence interval is between 0.4408 and 0.5184. And consequently, we fail to reject the null at the 5% significance level. Okay, so that's just an illustration of how to get to doing a hypothesis test in idle. Okay, now throughout this material we've been computing p-values based on z-scores, but really we ought to have been using t-scores for the mean-related, for the non-proportion data. For the proportion data, because the standard deviation is dictated by the proportion, by the mean, you do use z-scores, but for other kinds of data sets where the standard deviation is computed after you know the mean from the data, you really should be using t-scores. But the logic of doing the calculations to get your p-values and confidence intervals is the same, just substituting in t-scores for z-scores. Our data sets in all of our examples have had degrees of freedom significantly greater than 30, and in that case, the value that you get using a z-score will not be that different from, will not be terribly different from the value that you get using t-scores. Okay, so suppose that we compute a t-value for a two-tailed test, and the p-value is 0.015. What is the minimum value of alpha for which we're going to reject the null hypothesis? Well, because this is a two-tailed test, and our p-value is 0.015, remember that we have to double the p-value for, to account for each tail. So that if we double this p-value, it's going to be 0.03, and therefore the alpha would be 0.03. We're asked what is the corresponding z-score cutoff for this test, and we can use our critical value widget to figure that out. Because this is a proportion test, we do use the normal distribution, not the t-distribution. And for an alpha of 0.3, our critical value is going to be 2.1701. Okay, so that